Hello guys, and welcome back to my biochemistry fan fiction. I can't say that with a straight face. Welcome back to my biochemistry channel. So today we're going to be going over protein structures. So let's look at some basic terminology. So the first thing we're going to be looking at is polypeptides. So polypeptides, or as you can call them, polypeptide chains, are amino residues attached via one another via peptide bonds or amide bonds. So I have a generic protein structure right here consisting of just random amino residues. The polypeptide chain is the bond between the carboxyl and the amide, and I have that labeled in red right here, and it's either called the peptide bond or the amide bond. The alpha carbon, of course, is right here, which I showed you in a previous video. This is your amino terminus, which is always the beginning of your polypeptide chain. It will always be the nitrogen, the amide group. And then this is your carboxyl terminus. Your carboxyl terminus is always the ending of your polypeptide chain. Each amino acid weighs about 110 grams per mole. There's usually between 50 to 2,000 amino residues present on a polypeptide chain. So if you do the math real quick, that'd be about the lightest polypeptide chain you could have would be about 5,500 grams per mole. The backbone right here is actually the repeating portion of the polypeptide chain. So that's going to be your amide groups, your carboxyl, your nitrogen, all that good stuff. And the backbone is where the hydrogen bonding occurs. The hydrogen bonding actually occurs between the hydrogen present on the nitrogen and the oxygen present on the carboxyl group right here. Like I said, you always start with the amino terminus and you always end with the carboxyl terminus. So moving on. So looking at the peptide chain a little more in depth, the polypeptide chain, once again, is right here between that nitrogen and the carboxyl group. The polypeptide chain cannot be bent or rotated due to double bond resonance. So it can form a double bond, and that's why you can't rotate it nor bend it. And that double bond, you can see, forms when this excessive electron pair right here donates itself in, and then the carboxyl double bond here donates itself up to the oxygen, giving you this structure with the nitrogen being positively charged and the oxygen being negatively charged. Now, you can actually rotate the bond at your phi and psi bond. The phi bond is on the left, the psi bond is on the right of the alpha carbon. So I'll show you in the next slide. So once again, here's your phi bond on the left and your psi bond on the right, and rotation is permitted here. Now there are various rotational angles that are more desired than others, and you can actually use what's called a Ramachandran graph to locate what angles are most desired. Now on the left, the y-axis is going to consist of your psi bond, and the x-axis is going to consist of your phi bond. Now these dark portions, the green portions right here, are where your desired bond angles are located at. So for example, if you had a protein that was right here, you would have a psi bond that was negative 45 degrees and a phi bond that would also be about negative 45 degrees. And that would be a preferred bond angle for both of those bonds. Up here, you would have about 135 degrees for your psi, and you would have negative 135 degrees for your phi. I think you guys understand how to read these. You basically just go towards the left and go downwards, and that's then the angle for your psi and your angle for your phi. And it's the darker portions that have the desired angles. So moving on, looking at primary structure. Now primary structure is the simplest protein structure we're going to look at, and that is just your linear polypeptide chain consisting of your amino residues. So right here is a primary structure consisting of alanine, histidine, and serine. And as you can see, it is just a linear polypeptide chain with the amino residues attached to it. That is a polypeptide, or that is a primary structure, the simplest of the structures. The next simplest structure is what we like to call a secondary structure, and this is when that hydrogen bonding occurs between that backbone to form your beta sheets and your alpha helixes. Where's that word at? Alpha helixes. And do remember, Dr. Waglay's fun fact of the day is alpha helixes are right-handed only. As you can see here, I have two photos. This would be your beta sheet right here, and you can see the hydrogen bond occurring between the hydrogen on the nitrogen and the oxygen carboxyl group. Right there again, right there again, right there again, and that forms that beta sheet. Right here we have an alpha helix, which is I like to think of it as a spring-like structure. And once again, that hydrogen bond occurs between the oxygen and the hydrogen on the nitrogen. And there you go. Now, beta sheets can either be parallel, anti-parallel, or mixed, and they can either be flat or twisted. So something you need to know, proteins are usually found in globular structures, so big globular structures, kind of like think of myoglobin, just a big glob of protein. And they have to be able to reverse and turn themselves and loop around in order to avoid running into each other. So they do this via something called reverse turns and loops. And this would actually be a reverse turn right here, because if it kept going, it might run into itself if there was, say, another polypeptide chain up here. So this would be what we like to call a reverse turn, because it reverses itself back around. A loop, I have to show you another diagram for. A loop would be like this right here. And now then, this actually then exposes some of the protein residues, the amino residues, to the environment. And if you recall from my first video, what type of protein or amino acids would you find that are facing out towards the environment? Would they be polar or non-polar? I'll give you a second. If you answered polar, you're correct, because that means polar amino acids are hydrophilic, and hydrophilic acids that are exposed to the environment are usually interacting with water. Hydrophilic, water-loving. So remember, your hydrophilic polar amino acids are always on the exterior of your polypeptide chains, and your non-polar hydrophobic proteins are on the interior, so they'd be like in here and here. Once again, you start with your N-terminus and with your carboxyl terminus. This is a pretty complex structure, but you understand it. So coiled proteins. These are strong fibrous proteins constructed from 2 or more alpha helixes. So these coiled proteins, as you can see here, 2 alpha helixes that interact with one another via van der Waals forces. If you remember what van der Waals forces are, those are basically induced dipole moments. The closer those neutral atoms come to one another, they'll begin to induce a charge on the opposite molecule. And that actually can occur via asymmetrical electrical charges on the 2 atoms. Coiled proteins are usually found in keratin. Keratin is usually found in your hair, nails, skin, skeleton, stuff like that. But yeah, coiled proteins. 2 or more alpha helixes attached via van der Waals forces. Collagen. So collagen only has glycine on its interior. So glycine is on the interior of this collagen molecule only. And collagen usually consists of only glycine and proline, and the proline is actually helps stabilize it via steric repulsion. And what else also stabilizes it is hydrogen bonds will actually form between these 3 polypeptide helical structures. So collagen isn't actually consisted of alpha helices like the coiled structure. It's consisted of helical-like polypeptide chains. So these aren't actually alpha helixes. They're just helical-like. Glycine is at every 3rd terminus. So it goes glycine, proline, proline, glycine, proline, proline. And like I said, the repulsion from the proline stabilizes the structure, and there are 3 chains form the H bond. So these 3 chains are held together via hydrogen bonding, and then these collagen molecules can go on to form a giant overall collagen fiber. So the tertiary structure is our next structure we're going to be taking a look at. And now the tertiary structures are your 3D structures that usually occur due to R group interactions such as disulfide bonds. But these are your 3-dimensional protein structures. Myoglobin is an amazing example of a tertiary structure. And a disulfide bond, what exactly is that? A disulfide bond occurs between the sulfur present on cysteine, and when it does form this bond, it turns into cysteine, and this can actually then be cleaved via something called beta-mercapephenol. I can't really pronounce that very well, I apologize. Beta-mercapephenol. So, moving on, cumulative selection. Proteins don't actually fold randomly, they actually fold via increasing stabilization. Well, progressive stabilization is the scientific term for it. But basically what that means, to simplify that, is cumulative selection when it comes to protein folding is think of the incorrect folded proteins are less stable, so they're going to get kicked out of the structure. They're not going to stay there. The correctly folded proteins will be retained because they're more stable. So over time, you'll have more overall correctly folded stable proteins and less incorrectly unstable proteins. So then eventually you'll just only have stable proteins because those incorrectly folded proteins will keep getting kicked out due to them being less stable than the correctly folded proteins. And the graph that goes with this is right here. And as you go down, the protein is more and more correctly folded due to there being less entropy, less randomness. And as you go up, there's more entropy and it's less stable, and there's less correctly folded proteins. So at the bottom, you're going to have your most stable protein structure, and at the top, you're going to have your least stable protein structure. At the top, you're going to have the highest amount of entropy, and at the bottom, you're going to have your lowest amount of entropy. So some terminology before we go. Domain is identical protein structures. Motifs are supersecondary structures. So supersecondary structures are structures that consist of two secondary structures attached to one another. So think of the coiled proteins, the two or more alpha helixes attached to one another via van der Waals forces. Those would be motifs. Intrinsically disordered proteins are proteins that have no formal structure until they interact with another molecule. Metamorphic proteins can exist in various conformations, each with the same amount of energy. So with that being said, guys, I hope you guys have a wonderful night and you guys stay frosty.